Hello, this is the next session in the course on artificial intelligence. So, in the last class, we spoke about uninformed search strategies. So, when we talk about problem solving, we are going to find a series of actions, a sequence of actions which takes you from the start state to the goal state. So, when searching for these actions, you get the search tree, and from the search tree you are going to find the series of actions or a path from the start state to the goal state. So, the way we search this search tree varies depending on the strategy that we are going to use. So, when we talk about uninformed search strategies, we are not using any information about the particular problem at hand, whereas in informed search strategies, we will be using information about the problem at hand. Okay? In other words, you have some specific knowledge about the particular problem which you are going to solve, and you are going to use that information to cut down on the search so that you get a solution much faster. Okay. So, this strategy is called the best first search. So, this best first search is something like the depth first search and the breadth first search we had. This is known as the best first search. So, here basically every node n will have an evaluation called f of n, and this evaluation is the one which is used, and the one which has the lowest evaluation is the node which is expanded at every point in time. We know that all the leaf nodes together form what is called the frontier, and in this frontier one of the nodes has to be selected to be expanded. So, to select this node which is to be expanded, we use this evaluation function f of n, and in the frontier whichever has an evaluation which is the lowest out of all of them will be the one which is expanded at every point in time. So, basically this is the program or the pseudocode is exactly like the uniform cost strategy which we used in the uninformed search, but there we used g of n instead of f of n, and then the smallest one was removed from the priority queue at every point in time. So, here also you are going to do the same thing, except that you are going to take the node which has the smallest f value and not the g value. Okay. So, the choice of f determines which strategy you are going to use over here. Obviously, when we say f, okay, there are two values which are there in that. So, f will be equal to g of n, f of n will be equal to g of n plus h of n. So, h of n depends on the heuristic function, okay, and it is the estimated cost of the cheapest path from the node n to the goal state. So, note that this is the estimated cost, not the real cost, because we do not know the real cost. If we knew the real cost, then there was no need of any search, right? We already have the solution. But this is the estimated cost of the cheapest path from this node to the goal state. How do we calculate this heuristic function? Like we said, we are using some problem specific knowledge over here. So, for example, when we speak about this road map which is over here, and if we want to move from Arid to Bucharest, right. So, suppose you are at Arid and you want the heuristic function, okay, that is the cheapest, the evaluation of Arid when it comes to Bucharest. So, what you use is you use what is called the straight line distance, or like they say the distance as the crow flies, right. So, you are going to use the distance between Arid and actual distance between Arid and Bucharest. Of course, you can't go along that because you have to go only along the roads which are there, right. So, this distance from Arid to Bucharest will be less than the actual distance from Arid to Bucharest, but we will use it as a heuristic. Okay, so which will help us to know whether how far Arid is from Bucharest, right? So obviously, if you take the goal state will have a Hn value equal to 0, okay, because it's already at the goal state. So the distance of this node n from the goal state will be 0, right? So this is h of n in this particular case, right? So like I said, there are many strategies here also. You have what is called the greedy best first search. So the greedy best first search only uses this heuristic function h of n, okay. So it tries to see from the present position which is the best way to go, okay. So that's why it is called the greedy algorithm. So if we look at this particular figure here, it gives you the straight line distance from all the cities to Bucharest, okay. So suppose your goal state is Bucharest, then you need to have the straight line distance from all the cities, okay. We know that there are 20 cities, right? So from all these 19 cities, what is the distance, straight line distance from there to Bucharest? So if we have this, okay, then if we try to move from Arid to Bucharest, we know that there are 3 possible ways of doing it. So you will be moving either to Zarind or okay, so you will be moving either to Zarind or to Sibui or to Timisoara. So now from these 3 points, you have to say what is the distance to Bucharest, okay. So if we look in this, we can see from Timisoara it's 329 is the distance, and the other 2 are Zarind and Sibiu. So from Zarind it is 374, Sibiu it's 253, right? So we can see that 253 is the smallest out of these 3 values. So that is the h value of Sibiu. So suppose I take the h values, so and I put these h values in a priority queue and take out the smallest one. So you will be moving from Arid to Sibiu, and then from here again you take all the possible edges that go out from here, okay, except that you don't go back to Arid, right? And then out of these you choose the, so what you will have is 151, 99 and 80. Sorry, you will have the distance of this point from here, of this point from here, etc., right? And then you have to choose from the frontier the one which has the smallest straight line distance. So obviously the whatever straight line distance we are taking is somewhat correlated to the road distance, right? So city which is closer to another city will definitely have a smaller distance even on the road. So if we take this particular figure, it tells you how this actually goes from here. So we can see that from Arid there are 3 possible places to go, and out of these we can see that Sibiu is the smallest, so that is taken and expanded, right? And when you expand you get all these, so Arid is left out and you get all these 3, and you can see what is a straight line distance from these to Bucharest, right? So these are the values. So we can see that the nodes are labeled with their h values, okay. So we take this will be the frontier. Okay, so these three nodes and these two nodes together will form the frontier, and from this the one which has the smallest is Fagaras, so that is taken and then it is expanded in the next step. Okay, so this is how the greedy best first search will work. Okay, so in the greedy best first search we are using only the H value. Okay, and we know that in the uniform cost strategy you are using only the G value. Okay, so that is the distance from the start state to the node N. So this is it's called greedy because at each step it tries to get as close to the goal as it can, right? So that's why it is known as the greedy best first search algorithm. Okay. So what happens is that sometimes it does not give you the optimal strategy. For example, if we take moving from ERC to Bucharest, since so if you look at the straight line distance from these two, okay, from these two, what is the straight line distance? Okay, this has 234 is the straight line distance, okay, and this has 199 as the straight line distance, okay, this Vasily. So what happens is that sometimes if you are taking the uniform cost strategy, you find that it would have chosen this point instead of choosing this point, okay, but this point actually is a dead end, okay, you can't go anywhere beyond that, so you need to come back this way, right, and it may not even be able to find the solution. So what I am trying to say is some of these heuristic values that we use may not give you a solution at all, but in most cases you find that you are getting the solution and you get it much faster. Okay, so if we look at the greedy best first search algorithm, the worst case time and space complexity is order of B to the M, where M is the maximum depth of the search space, okay. But this is the worst case. So what you find is if you are using a good heuristic function, it may not go to the worst case, okay. So the complexity will be, actual complexity will be much less, it's reduced a lot, okay. So it doesn't need to expand so many nodes, and the amount of reduction depends on the problem and the quality of the heuristic that you are going to use. Okay, now the A star algorithm is the most popular algorithm over here, okay. And what is the A star algorithm? It's again a form of best first search, or you can say it is best first search, okay. They sometimes call A star algorithm the best first search also. So here it evaluates the node by combining G of n, the cost to reach the node from the start state, and H of n. So H of n is the cost of getting to the goal, estimated cost of getting from this node to the goal state. So f of n is equal to G of n plus H of n. So once you get f of n, you are going to, the algorithm is exactly like the uniform cost strategy which we saw in the uninformed search, except that f will be replacing the G value which we used over there, okay. So this actually is taking both things into account. It's taking the cost of getting to this node from the start state and also the cost of, estimated cost of reaching the goal state from this state, and it's found to be giving a good solution, right. So we need to see, if we look at the function H of n, what are the conditions that it needs to satisfy, right, because there may be a number of heuristics that are available. Now what are the heuristics which we should use and what are the heuristics which we shouldn't use. Okay, so that is what we need to actually see over here, right? So what are the conditions for optimality? In other words, are you using the optimal h of n? That is what you have to see. First of all, it should be a admissible heuristic. So what do you mean by a admissible heuristic? An admissible heuristic is one that never overestimates the cost to reach the goal. For example, if we take a node n and we say that we are taking h of n to be the straight line distance between that node and the goal, the actual distance from this node to the goal will be the distance along the road. So obviously it will be larger than the straight line distance. So because of that, it's a admissible heuristic. Okay, so it does not overestimate. Okay, that's what we need over here. Okay, so if you do that, then you know it will not, in other words, that it's going to at some point or the other reach the node which is the goal state if you do this. Okay. So if we see yeah, so this is the A star algorithm and it shows how it actually works. So we have arid and these are the three that you have, and this gives you the j of n and h of n. Okay, so this is your g of n plus h of n. So we can see that the smallest among these is this one, CBU, so that is going to be expanded. So here let us leave out arid, and this is going to give the f values for these three nodes, right? So now we have all these nodes in the frontier, and what is the smallest out of these? The smallest is 413. Okay, so that is this one. So this node is taken and it is expanded, and when you expand these, you are getting these nodes. So what are you taking as your G? Okay, so when you come from this point from here, you are taking the distance from arid to CPU as your G value, and the G value here would be the G value here plus the distance from this point to this point. So in that way you can calculate the G values. So if we look at the ones in the frontier at this point in time, you get 415, I think, is the smallest, right? So you are taking this Fagaras and you are expanding that, and you are reaching Bucharest over here. Okay, but what you are going to do is that you are not going to immediately stop at this point in time. Okay, so you are going to only decide at the time of expansion where you are going to stop. Okay, so now once you do this, this one gives you the next smallest one, so you are expanding that, and once you expand that, you are reaching Bucharest, right? And this has f value of 418, which is smaller than the f value we got in this goal, right? So this would be your proper goal. Okay, so this is your goal, and you can backtrack and get the path. So you need to go to arid to CBU to this value, then this one, and then you come to Bucharest. So this is how the A star algorithm basically works. Okay, so another thing that you need to see is the consistency. Okay, so what happens is that as you go down the search tree, okay, so suppose you take h of n, okay, of some node n, okay, and one of its successor is n dash. So the heuristic of h of n dash, okay, should be greater than the heuristic of h of n, because you are adding that extra distance from that node to that node, okay, the cost from that node to that node. So this is an inequality which needs to be satisfied, that h of n is less than or equal to the this value, okay. So if this is satisfied, then you say that it is consistent. In other words, it is following the monotonicity, okay. So actually h of n should be less than h of n dash. So that is what you have to see over here. So if these conditions are satisfied by h of n, then it is an admissible heuristic. If it is not an admissible heuristic, what is going to happen? It's possible that if it's not an admissible heuristic, as it goes down searching for the goal, it may miss the goal altogether, because when we are using a heuristic, we are seeing that we don't expand all the nodes, okay. So when we overestimate the heuristic, you may actually miss the goal. So it may miss that goal state completely and go beyond it, right, which then becomes difficult because we need to find the goal state. Yeah, so we can say that for A star algorithm, the tree search version is optimal if Hn is admissible, okay, and the graph search version is optimal if Hn is consistent. In other words, if the consistency and admissibility of Hn is maintained, then the program is going to be consistent, okay. Now what happens is that since we are talking about f cost, okay, in other words we are talking about f which keeps increasing, okay, so f is the cost of reaching that node, right. So what happens is, if you draw contours, okay, so that all the nodes which have the same f cost, okay, are connected together, you will get something like this, right. So we are starting from arid, and this is with f cost is equal to 380, f cost is equal to 400, f cost is equal to 420, etc., right. So what you find is you get contours in this way, okay, and looking at the type of contours you have, you can see whether the search is good or not, right. So so what you are getting basically is something like ellipses in this case. Okay, so what you find is that uniform cost strategy, if you are using the cost, you are going to get circular bands, but here you find bands which stretch towards the goal state basically, okay. So now if C star is the cost of the optimal solution path, okay, then A star expands all nodes with your Fn less than C star, okay, and it reaches the point where Fn is equal to C, but it will never expand anything where Fn is greater than C, okay. So this shows that you will be reaching the optimal solution basically. So what you are doing is you are pruning out some parts of the tree. So that is what we need to see over here. Okay. So the A star algorithm is optimally efficient for a consistent heuristic. In other words, this means no other optimal algorithm is guaranteed to expand fewer nodes than A star, okay. So that is what we need to see. But what happens is that if it does not expand all the nodes, okay, which has f cost less than C star, then you may actually miss the optimal solution. So that is very important to see over here basically. So there are variants of A star that find suboptimal solutions. Okay. Okay. A star also has problem with the complexity, but it is much less as compared to the breadth first search and the breadth first search that we spoke about. Next algorithm we'll talk about is the memory bounded heuristic searches. There are a number of heuristic searches which are bounded as far as the memory is concerned. And just like we had the iterative deepening algorithm earlier, okay, here we talk about the iterative deepening A star algorithm. So there we used the depth up to which we are going. Okay, so we started with the depth is equal to 0, depth is equal to 1, 2, 3, etc. Whereas over here we talk about the cost, the f cost, okay, so the f g plus h. So that's what we are going to use over here. So what you do is first you start off with a smaller f cost, then you keep increasing your f cost at every point in time, okay, and instead of increasing the depth you are increasing the f cost. So that is what leads to the IDA star algorithm over here basically. Okay, another one is what is called the recursive best first search. Okay, here the algorithm is shown where you are using a recursive formulation over here. Okay, so recursive best first search is basically used over here. So what is done here is it's similar to the recursive depth first search, but it uses the f limit variable. Okay, if it exceeds the limit, okay, then the recursion unwinds back to an alternative path. Okay, so that limit is used. So recursive depth first search is a way of doing the iterative deepening A star algorithm. Okay, so this shows how the RBFS searches through and reaches the solution that you are looking for. So you can see here that once something else becomes better than this, then it is cancelled out, and the value in its leaf node, okay, which is the smallest, is noted there, right? So once we come here and we come to 417, we are not stopping here, right? So we come back, and if we look at the nodes in the front here, you will see that this Fagaras has a smaller value. So what you do is that you're removing these nodes and you're storing this 417 at this point in time, and you're expanding this one. Okay, so once we expand this, we find that this 417 is the smallest after that. So what is done is that here this one is removed, and this 415 you're storing this smallest 450 there in this subtree, and you're coming back to this and expanding this, and you find that you get the Bucharest here, which gives you the smallest path from Arid to Bucharest. So the problem is over here is that it may keep changing its mind, right? So it says this is better, then it changes its mind, and it says that is better, and then again it changes its mind and comes back to the original one. So in that you find that there is some time that is spent in going from one node to another node and then coming back to the same node again. So there are two more algorithms which are called the memory bounded A star and the simplified memory bounded A star. So we'll continue talking about this in the next session. So we'll stop this session here. Thank you.